Solving inequations. So we know an equation like 3x is equal to 12 has one solution. It's when x is equal to 4. So when the equal sign is replaced by less than or equal to, is greater than or equal to, this results in an inequation, basically meaning that we have a bunch of different answers that can make this true. Okay, so like 3x, okay, as we said, is greater than 4. Okay, 3x is greater than 12. So what values of x make this true? Whenever x is greater than 4. Okay, so we solve these just like a regular equation. Okay, and we know if I substitute anything that's bigger than 4 into my original equation, so let's try 5. So 3 times 5, that should be greater than 12, and it is in fact true that 15 is greater than 12. Okay, so solving an equation just means that we solve it like an equation. Now, what is the meaning of less than? Like, we always say, you know, a number is less than the other, but what's it actually mean? What's it actually look like? So geometric interpretation says that, well, if A is less than B, then A is on the left of B on the number line, okay? So a number line, okay? So we know that 2 is less than 5, and that is because 2 is less than 5 on the number line, okay? It's further to the left, okay? And we say that if A is less than B algebraically, that is that B minus A is positive. So the bigger number minus the smaller number will be a positive answer, okay? So that's pretty straightforward. So solving linear inequations, use the same method for solving solving a linear equation, except that. Now the only difference is when we multiply by a negative or a positive, we have to swap the sign. So negative 3x is greater than 12. So if we were just to solve this regularly, we'd divide both sides by negative 3, and we'd be left with x is greater than 4, okay? Oh, sorry, negative 4. So that means that any number that's bigger than negative 4 would make this equation work, like the original one. So a number that's bigger than 4, well, let's try x is equal to 0. And that's a number that's bigger than negative 4. If we put it back up into here, we should get negative 3, lots of 0, is greater than 12, which means 0 is greater than 12, which we know is not true. So whenever we multiply or divide by a negative, okay, we have to swap the way that the sign is facing. So 3x is greater than 12, then x is less than negative 4, okay? So then you can try like negative 5 or negative 10, put negative 10 into there, 30. So negative 3 times negative 10 is 30, 30 is greater than 12, okay? So that's just the property of dividing and multiplying by negatives. Now, when you solve a quadratic equation, the easiest way is to graph the associated parabola. So move everything to the left-hand side and then sketch the graph of y is equal to the left-hand side, showing x-intercepts. Now you can read the solution off the graph. So if we're looking for when the graph is greater than or equal to 0, then you're looking for everything above the x-axis. And then if it's less than, then you're looking for everything that's below. And it's just pretty simple. So we'll look at an example in that in a bit. Solving absolute value equations and inequations on the number line. Now, what we're going to do is we're going to force the equation. Also, it's best to treat them like as their distances. So we force the equation or inequation to be one of the following forms. So that is x minus b is equal to a, or x minus b is equal to less than, or like, you know, in some form, it's the absolute value of just x by itself minus some constant, okay, and is greater than or less than or equal to a different value. And then we find the solution using a distance on the number line. So we'll have a look at an example of that in a moment too. Solving absolute value equations and inequations algebraically, when we are solving f of x is equal to the absolute value of a function is equal to some value algebraically, we know that we just write that as the function is equal to the positive and the function is equal to the negative, because we know that no matter what's on the inside of an absolute value, okay, it's always going to give us a positive answer back. So when we've got these ones here, so these the absolute value of f of x is less than a, or the absolute value of f of x is greater than a, then all we need to do is just rewrite it in one of these two ways. So if it's less than a, then we just rewrite it as minus a, or f of x is between minus a and a. And if it's greater than a, then we just write it as f of x is less than negative a, or f of x is greater than a, okay? And it's just, you treat it as if it's like cases. Now, just like when we had f of x is equal to a, and f of x is equal to less than a, there have no solutions because we can't have the negative values of an absolute value, okay? And then that's the value of f of x is greater than a is true for all values, okay? And last but not least, solving inequations with a variable in the denominator, okay? So you are allowed to do this and it works quite well. We can move the bottom of an absolute value, and you can do this with regular equations too, but you can multiply both sides by x minus 4. So if I multiply the left-hand side by x minus 4 and the right side by x minus 4, okay. The only problem with this is that sometimes x minus 4 can be negative. So let's try, if x is equal to, 1, then 1 minus 4 is equal to negative 3. Okay, and if I divide by negative 3, well, that changes this sign here. And we don't really want to do that because that means that we'd have to have two different problems that we'd have to solve. And, it can get quite tricky if we do it like that. There is an alternative way to do it, and it's just to multiply both sides by the square of whatever's on the denominator. So if we've got 5 over x minus 4 is equal to 1, what we can do is we multiply both sides by times both by x minus 4 all squared, okay? And we know that x minus 4 all squared has to be a positive number or 0, but we know it can't be 0 because you can't have 0 on the bottom of the denominator, but we'll talk about that in a sec. But x minus 4, doesn't matter what value I put in, I'm always going to get a positive number back out. So this greater than or equal to sign will always stay as it is. Well, unless there's something that we need to do in a bit later. But doing that, we get 5. It'd be, so if I'm timesing the top by x minus 4, okay, that gets rid of one of them, and I'm left with 5 lots of x minus 4. Might write this out algebraically, actually. So we go 5 over x minus 4 lots of x minus 4 squared is greater than or equal to 1 lot of x minus 4 all squared. So this one here cancels with one of these ones here, and that leaves me with 5 lots of x minus 4 is greater than or equal to, and then 1 times x minus 4 all squared is just x minus 4 all squared, okay? And then following it out, we can get a solution like that, and we can then work out what it is using our thing, okay? So what we will do, bell's going at very inopportune time, we'll have a look at that in more detail with our last example that we'll go through. So with that being said, let's have a look at some examples. Example number 1, solve and sketch 4x plus 2 is greater than or equal to 6x minus 10. So what we're going to do for this one is we are literally going to rearrange it as if it was like a regular equation. Okay, so 4x plus 2 is greater than or equal to 6x minus 10. Now, normally what I would say is we're going to move everything to the left-hand side. So what I normally say when we solve these types of equations is look for which side has the more x's and then move everything over to that side. We're not going to do this in this case. What we're going to do is we're going to move all the x's to the left-hand side and everything else to the right-hand side, okay? So to do that, what we're going to do, I wonder if I can get a new color. We're going to minus 6x. I'm going to minus 6x from both sides. Okay, so when I do that, I get negative 2x plus 2 is greater than or equal to negative 10. Okay, now solving this equation like we normally would, I would subtract 2 from both sides, minus 2 minus 2, that leaves me with minus 2x is greater than or equal to minus 12. Okay, now I'm going to divide both sides by negative 2, and when I do that, remember, it swaps the sign around, and it gives me that x must be less than or equal to 6. Okay, so with that being said, I just need to sketch it, so minus 6 on the number line. Now because it's less than or equal to, I'm including it, so I circle this, the middle in, or the bit in, and then it's going to the numbers that are smaller than negative 6, as x is less than negative 6. Okay, part B. So we're going to sketch. Now this one's a little bit different. We've got 15 is greater than 3 minus 2x, which is greater than 11. Okay, now typically we wouldn't write something like this, but you'll see why we have in a moment. So you can just treat this like this is two things. So if you can't see my thumb, but if I cover up that and I'm left with, so I just remove that and just look at what I've got on the other side. I've got 15 is greater than 3 minus 2x. So what we would normally do to solve this is we would, subtract 3 from both sides, okay? But the problem is we've also got this 11 that's on the other side. What we can do is we can just subtract 3 from everything, okay? And we just treat it like as if it was two equal signs. And what you do to one side, you do to the other. And alternatively, what you do to one side and you do to the middle, you also do to the third side. So we get 12 is greater than. So minusing 3, we get minus 2x. Okay, and which is greater than 8. Now we're going to divide both sides by -2. Or all three sides by -2. So divide by -2, divide by -2, divide by -2. Now when I divide, it swaps my signs around. X is in the middle, -4 and -6 like that. And that gives me a much better statement. 6, or X is between -6 and -4. Okay, and so that's how we do those ones. Okay, example number 2. We're going to solve each inequation by constructing a function and sketching it. So we're actually going to make a function. We're going to sketch some, as you can see, some x squared terms, so it's probably going to be parabolas. Okay, and so we're going to do that. So when we're doing this, move everything to the left-hand side, okay, and then divide everything through by the coefficient of x squared just to get what it's going to be. So let's start with A. So x squared is less than 16. Well, we know that's the same as x squared minus 16 is less than 0. Now notice that the sign of my inequality doesn't change because it only happens when I'm when I'm multiplying or dividing by a negative. If I'm just subtracting 16, it doesn't do anything. So that leaves me with that. Now, what we're going to do is we're going to sketch. So we're just going to do a quick sketch. It doesn't have to be anything really neat, but we're going to sketch x squared minus 16 is equal, well, let's do it properly. Y is equal to x squared minus 16. So it's just everything on the left-hand side. So that's why we want to move everything across. So when I sketch this, it's not going to be an issue. So x squared minus 16, so my roots of that are, I'm going to go underneath the slide. If we factorize this, we get x plus 4 and x minus 4, okay? Two numbers. So difference of two squares, x plus 4, x minus 4. So my two roots are when x is equal to -4 or when x is equal to +4. So we've got something like that. We know it's a negative. I don't really care. All I really care about is where my y-intercepts are, okay? So this is y is equal to x squared minus 16. Now, our original function is, or our original inequation is x squared is less than 16 or x squared minus 16 is less than 0. So we're looking for the values where this function is less than 0. Okay, so whereabouts is this function less than 0? Well, we're just looking at the line and we're looking where it's less than the x. And as you can see, it's less than the x in these parts here. So where is that? Well, they're just between -4, so when x is less than, when x is greater than or equal to, just greater than, because we're only using greater thans in this one, or less thans in this one. So when x is greater than 4, or x is less than 4, okay? So another way to write that, when x is greater than -4 and x is less than 4. So another way of writing that is -4 is less than x is less than 4, okay? And so that's the solution to this one here. So it's basically, where is my sketch lower than the x-axis? Okay, and we can see that between -4 and 4, so these 2 points here, it's all lower than the x-axis. Okay, part B, 5x plus 6 is less than or equal to x squared. Okay, so again, we're going to move everything to the left-hand side. So when I do that, I get minus x. Well, actually, I'll tell you what, because we don't really want to minus in this, we might move everything to the right-hand side, and we'll do one of our tricks. So if I move x squared and 5x and 6 to the other side, okay, I'm going to get x squared. Oh, no, we'll do it the way. Move the x squared across, we get minus x squared plus 5x plus 6 is less than or equal to 0. Now we're going to divide everything by a factor of -1 to remove the negative in front of the x squared. So it's going to give us x squared plus, or sorry, not plus, so opposite of plus is a minus, it's minus 5x and a minus 6. And when we divide everything by the negative 1, we just have to flip the sign around. So we want the values when x squared minus 5x minus 6 is equal to 0. So what we're going to do is we're going to sketch y is equal to x squared minus 5x minus 6. Okay, so to do that, we're going to factorize this sucker. That's a nice easy one. Two values that multiply to give negative 6, but add to give negative 5. Hopefully you got negative 6 and positive 1. Okay, so just doing a quick sketch again, it doesn't have to be Picasso. So we know that x is equal to, so the values where x is equal to 0, so when y is equal to 0, x is equal to 6 or negative 1. Okay, so my values, or my roots for this thing are at negative 1 and 6. Okay, so my parabola is going to look something like that. Now, going back to our original equation, we're looking for values where 5x plus 6 is less than or equal to x squared, or when negative x squared plus 5x plus 6 are less than 0, or when x squared minus 5x minus 6 is greater or equal to 0. Now, I recommend doing this one because this is the one we ended up sketching. So this is the sketch we've got. X squared minus 5x minus 6 is greater than 0. When is this function greater than 0? So when is my graph greater than 0? Or in other words, when is it above the x-axis? So a shortcut to do it is literally go, okay, if I'm here, do I need to go up or down to hit my function? Well, if I need to go down, that means I'm in a negative. So all of this part between negative 1 and 6 are negative. Whereas over on this side, okay, over here and over here, so beyond the 6 and back past the negative 1, where my values are positive or greater than or equal to 0. So because it's greater than or equal to this time, we're going to be using the greater than or equal to or less than or equal to signs. So the values for when this is true are when x is less than or equal to negative 1, because here's the negative 1 here, and all the values where this thing is greater than 0 are to the left, or when x is greater than or equal to 6. So again, here's my value of 6, all my values that are bigger than the x-axis or beyond the 6. So when that is x is greater than or equal to 6. Okay, so there's my two values that make this equation true. And just like with our regular inequations, we can test to see if this is true. So numbers that are negative 1 or 6 make this true. So let's check something that makes this false, which will be easier, because if we check 0, 0 should make the very first inequality that we had false. So what it's saying is 5x plus 6 is less than or equal to x squared. So if we try 0, this shouldn't be false because it's not part of the domain that makes this true. So if I put 0 into here, I get 5 lots of 0 plus 6, which is just 6. And that should be less than or equal to 0 squared, which is just 0. Is 6 less than or equal to 0? No, it's not. So it's not in our domain, just like we have graph down here. Wrong button. Okay, let's have a look at example number 3. Okay, so we're going to solve the equations and end inequations on the number line. So solve these equations and inequations on the number line. Okay, so let's start off with the first one. So we've got x plus 3 is equal to 2. So what this is basically saying is, so I'm going to rewrite this as x minus 3 is equal to 2. Because effectively what this is saying is the difference between x and minus 3 is 2. Okay, so what is the distance, or what distance between x and minus 3 is equal to 2? So what we're going to do is we are going to start off by drawing a number line. Now we want the difference between x and minus 3. Or in other words, what's the difference, or, what numbers are on either side, or the two distance away from negative 3. So we start with negative 3 in the middle. Now we want numbers that are 2 away either side. So that is negative 1 and negative 5. Okay. And so those are my two values. Okay, so I'm going to put a dot there and a dot there. Now this is just an equal, so it means that these are the two values that make this true. And we can test that too by putting them in. So if I put minus 1 into here, we get minus 1 plus 3. Okay, minus 1 plus 3 is 2, so the absolute value 2 is equal to 2. If I put minus 5 in there, I get minus 5 plus 3, okay, which is equal to negative 2, and the absolute value of negative 2 is equal to 2. But basically what we're doing is we're saying, okay, we want to find out what is 2 away from the negative 3. What are the values that are 2 away from the negative 3? Okay, so we know that the negative 1 and negative 5. Okay, getting a little bit harder. 2x minus 5, okay, is greater than 2. So when we've got something like this, again, we want it in the form where we've got x minus b is equal to a. Okay, that is, we've got what we want, x minus some distance is equal to the distance apart that they should need to be. Or x from some point is equal to distance, or in this case, it's the values where it's less than that. So what are the values between 2x and 5 that are less or greater than, in this case, sorry, not less than, greater than 2 away? Okay, so what we're going to do is going to divide everything by 2. And this is something you can do. And I know when we solve equations, we normally say do the opposite of BODMAS, so addition and subtraction first, but you can actually do this as long as you do it properly. I'm going to divide everything by 2, but that means I'm going to literally divide everything by 2. And that's going to give me x minus 5, well, the absolute value of x minus 5 on 2 is greater than 1. So 2x minus 5 is greater than 2. In other words, is by asking what's the difference? Well, what's the difference from 5 over 2, which is 1 away? What are all the values that are greater than the distance? X minus, well, from 5 on 2, yeah, basically. I don't think I explained that very well. But what are the distances? So if we start at 5 on 2, okay, which is between 3 and 2, what are the distances that are 1 away? Okay, so, or greater than 1 away. So 3 on 2 goes to then 7 on 2, so that's 1 away there. Okay, now I'm not going to circle this one in because it is not greater than or equal to, it's just greater than. Okay, and for the other one, it's 1 away from this way, so it's going to be 3 on 2. So the distance from here to here is equal to 1, and the distance from here to here is also equal to 1, okay? So we want all the values where the distance from 5 over 2 to any numbers along this number line are bigger than or greater than 1. So it's just the numbers that are on either side, okay? So let's try the number 0. Is 0 more than 1 unit away from 5 on 2? Well, yes, it is. It's 5 on 2 units away, which is 2.5, so it's much bigger. Okay, so let's say you do that one, and that's how we're going to do ones like this. Now C, very similar. Absolute value of 3 minus a half x less than or equal to 5. Now, when we do this one, okay, we're going to say, okay, well, looking at this one, we don't need to divide anything. In fact, we're going to times. So we're going to times everything by a half. So times by a half, times by a half, times by a half. Well, not time. Sorry. We're going to divide everything by a half, which is the same as dividing it by 2. No, God, sorry, there's so many noises distracting me. We've got timesing by a half, which is the same as, or the opposite is dividing by a half, which is the same as timesing by 2. Sorry. So 3 times 2 is equal to 6, minus x is less than or equal to 10. So what this one is saying now is that we want the distance from x to 6, okay, because it's just the difference. The difference is the distance. Doesn't matter which way the 6 and the x is, as long as we have a minus in between them, is less than 10. Okay, so the distance from x to 6 is less than 10. So here's my number line. Okay, let's start with the middle. The number that we're starting with in the middle is 6. We're concerned about the numbers that are 10 units either way. Okay, so 16 is 10 units above 6, and negative 4 is 10 units below the 6. Okay, now we're going to say to ourselves, well, what is the values that are less than? Okay, so is it, what are the values that are less than 10 units away? So if I went out over here, so if I pick 20, well, 20 is 14 units away from 6, so that's too many. So in fact, with this one, I'm including 16 and negative 4 because we've got the less than or equal to. But all the values that are less than are the ones that are in between. Okay, so for example, let's use 0. We can put that in the equation. We get 6 minus 0, which is equal to which is equal to 6. And 6 is less than or equal to 10. Okay, so, 0 is a number that works. And we can put that in there. So, with that being said, that's that example done. So it's everything that's in between those two, just like that. Okay, so let's have a look at example number 4. Okay, we've got some inequations that we need to solve. Okay, so we're going to solve... we've got some inequalities that we need to solve, and I'm just not happy. It's just not my day today. We've got some inequalities and some equations that we need to solve, but they're absolute value ones, okay? So we're going to use those rules from before. So the first rule is that if we have the absolute value of a function, so we're going to be using algebra to solve these ones, okay? So if we have the absolute value of a function, then we just rewrite it as f of x is equal to a, and f of x, so the function, whatever it is equal to negative a. So when we have the absolute value of a function, you just rewrite it as that equal to a and negative a. Number 2 was if we have the absolute value of a function, it's equal to some value, then what we do is we just put that function, and it's less than a, and then we put that function in the middle of the pack like that. And then last, our third rule is that if we have the absolute value of a function and we want the values where it's greater than a, then that just means that f of x, so we're going to rewrite it as our function is less than negative a, and our function is greater than a. Okay, so these are like our 3 rules that we're going to use to work out how to solve these. So if we start with part A, we've got 10 minus 5x is equal to 25. Okay, so because, what are you doing there? Because we've got a 25 and it's an equals to, okay, so I'm going to use rule 1. Okay, so you wouldn't actually have to write to use rule 1. I'm just doing this to show you guys what to do. So the absolute value of f of x is equal to a. So that means that f of x is going to be equal to a. So the function on the inside, so 10 minus 5x is going to be equal to the number on the outside. And that function is equal to negative of that as well. So let's continue by solving these two. So first things first, subtract 10. Subtract 10, we're left with minus 5x is equal to 15. Divide by negative 5, divide by negative 5. So x is equal to negative 3. So that's one solution to that inequality, or to that inequation, to that absolute value equation. This one we're going to subtract 10, we're going to subtract 10 just like we did before, so we get minus 5x is equal to negative 35, okay? And then we're going to divide by negative 5, divide by negative 5, and we get x is equal to 7. And that's my second value there. Okay, part B was then to solve it. So 10 minus 5x, but this time, instead of being equal to, it's less than 25. So we're going to use rule 2 for this one. So that is, we're going to rewrite it with f of x in the middle. So we're going to write it as negative 25 is less than our function, 10 minus 5 of x, which is less than, not a, 25. Okay, so it's in between the two values. We're going to solve it like we did with this other one as well. So start off with, okay, we've got minus 10. Okay, so minus 10. Minus 10. Sorry, I just got a notification on my Google Classroom. Minus 10, minus 10, minus 10. So it leaves with minus 35 is less than negative 5x, which is less than... not 25, that should be 15, okay? So negative 35 is less than negative 5x, okay? And then divide everything by negative 5, so divide by negative 5, divide by negative 5, Okay, so that gives me, okay, negative 35 divided is equal to 7. That is equal to x. That is negative 3. Now what we need to do is we need to then flip our signs around because we've divided by a negative. And we get 7 is greater than x, which is greater than negative 3. Or alternatively, we can rearrange this so it becomes x. And if we swap the 7 and negative 3 around their positions, okay, so remember there's a rule that if we swap x is greater, so if we have, like 3 is greater than 2, then 2 is less than 3. So if we swap them around, we also swap the signs around and we get negative 3 is less than x, which is less than 7. Or in other words, x is between negative 3 and 7. Now, I personally find solving them algebraic a lot easier than sketching these things, but it's up to you. You can use either way to do it. I'm sure your exercise will say, can you, use this method to do so, but we still have, in a test, it'll say solve this, and you can use either method, or in your HSC anyway. Okay, so last but not least, we've got the same equation again, but we've got it greater than. And so for this one, we're going to use rule number 3. So that is, we're going to split it up into 2 parts. So when I've got this, I'm going to rewrite it as my function is less than negative of that. And I'm also going to write my function as 10 minus 5x is greater than the positive version, okay? So it's kind of like you're doing the, when it's equal to it, but instead this time it's going to have a bunch of different values that will be the answers. So same as we did before, we'll just do the left-hand side and then we'll do the right-hand side. So we're going to get minus 10, get minus 5x is less than negative 35. So x, so if we divide it by negative 5 and divide it by negative 5, we get x is greater than 7. Okay, so any values that are greater than 7 will make that inequality up there true. Put in 10 minus 5 times 10, which is 50, so 40 should be greater than 25, which it is. Okay, then solving this side, so going through the same method, minus 10, we get minus 5x is greater than 15. So x, we're going to divide by negative 5 and divide by negative 5, just like we did. Swap the sign because we're dividing by a negative, and we get that x is less than negative 3. Okay, so then if you're asked to actually sketch that, okay, here's negative 3, here's 7, bang, bang, done. Like something like that. If you're asked to sketch it, but it's not necessary in this case. Okay, with that being said, we've got our last example. So this is an inequality that has a pronumeral in the bottom. So no absolute values for this one, just an inequality. Just a regular inequality. Now remember I said that we don't want to just move the thing to the other side. We're actually going to move the square of it. So if I've got 5 over 2x minus 8 is greater than or equal to 1, I'm just writing out big for me. Okay, I'm going to multiply both sides by 2x minus 8 all squared. So we get 5 lots of 2x minus 8 all squared over 2x minus 8 is greater than or equal to 1 lot of 2x minus 8 all squared. Okay, simplifying it out. Okay, so let me get a different color. Red. This guy's going to cancel with that one there. Okay, and now I can simplify this as 5 lots of 2x minus 8 is greater than or equal to 2x, or 1 lot of 2x minus 8 all squared. Okay, because 1 times 8 is just that. Now, we're going to expand this out to get 10x minus 40 is greater than or equal to, so 4x, 2x times 8 is 16, times by 2 is negative 32x, and then minus 8 times minus 8 is 64. Okay, now moving everything to one side, I'm going to do it this way this time and move everything to the right. That should be squared. And we get 0 is greater than or equal to, so the 4x squared is going to stay there. Negative 32 plus, so it's the opposite of plusing is minusing, so we're going to get minus 42x, and minus 40 over the other side becomes plus, and you get 108. and 4. Okay, so that is greater than 0, but then I can just rewrite this as 4x squared minus 42x. Let me write that a bit neater. Minus 42x plus 104 is less than or equal to 0. So if I flip them around, I flip the sign too. Okay. So we know about this thing there's some things that we know about this, but we'll come to it in a moment. What we're going to do now is we are going to try and sketch this, okay? So remember your rules for factorizing it. So we're going to try and sketch y is equal to 4x squared minus 42x plus 104. Now for this, I only care about the y-intercepts because I want to know if my parabola is negative between my intercepts or, well, I'll know if it's negative. It's going to be negative between my intercepts because it's a positive parabola, okay, positive parabola. So it's going to look like this. Here's my x-intercepts, okay, it goes like that. So it's going to be negative in between and positive above. If it's a negative parabola, it's going to be positive in between and negative above. So I know it's going to be negative between because I want the values that are less than. So I'm looking for the values between that makes this true. So to do this, we're going to factorize it. We're going to start off by factorizing out a factor of 4. That's going to leave us with x squared minus 13x plus 36 with the 4 on the outside, okay? And then we're just going to factorize the inside as is. So we get 4 lots of x minus, so 2 numbers that multiply to give to 36 and add to give to 13, or negative 13, so it should be negative 9, and x, so 9 times negative 4 should be equal to 36. Okay, so basically what this means is we've got this parabola now. It looks like this. Let me do that a bit nicer because this one's going to be a bit bigger. So we've got a parabola that looks something like this, where the y-intercepts are at 9 and at 4, okay? Now, the 4 at the front means that this thing is going to be a much steeper parabola. But again, as I said, I don't care about how steep it is. All I care about is where are these x-intercepts and where's it negative between them and outside of them. And so from here, we can pretty much answer our question. I'm looking for the values where my function up above, so 4x squared minus 42x plus 104 is less than or equal to 0. Or in other words, where is it below the x-axis? And we can see that in between 4 and 9, it's going to be below the x. So therefore, okay, the values of x that make the above equation true are when x is between or equal to 9 and between but not including 4. Now, why is it not including the 4? So why is it not including the 4? If we go back up to our original function, what happens when I put 4 into here? If I put 4 into here, okay, what happens? I get 2 lots of 4 minus 8, which is equal to 8 minus 8, which is equal to 0. Why can't I have an answer of 0 there? Because if I have an answer of 0, my equation becomes 5 over 0, which means it doesn't actually exist. There's no value there. So remembering that this is the function that we are trying, or this is the equation or inequation that we're trying to prove that, or we're trying to find what values work for that one. By doing all this algebraic manipulation, we can rearrange it to get it into a form where we can find x values that make it true, okay? So just doing all that algebra, this is, all these expressions are still true. The only thing that is different is that we just can't have 4 in here. So even though we do have a picture of a parabola here, on our original function, that 4 there wouldn't actually have a value. So the function would actually look something like that, where there's an asymptote going through that 4. Because remember, I have a function y is equal to 5 on x on 2x plus 8. This is the graph of a hyperbola. It looks something like that. We know that it has a vertical asymptote somewhere. It also has a horizontal one too. But we can find that by doing all this algebra, and we know by knowing the fact that that 4 there doesn't actually exist. So y not 4 can't divide the original inequality by 0. Okay, with that being said, that is the end for this one. I hope you guys can follow along all right, and there is no issues with you. I'm hoping all my answers are correct this time. See you soon.